Hi. So in this video, we'll discuss the second price auction, which is an application of the Bayesian game. Okay, and we will also argue and try to prove the Bayesian Nash equilibrium in the second price auction. Okay, so we consider a second price auction, which is called the second price sealed bid auction. Okay, so it means that in this auction, multiple bidders, they are bidding for some object, and their bids are sealed bids. So each player cannot observe the other player's bids. Okay, so they need to simultaneously submit their own bids. Okay, so this is a sealed bid auction. Okay, so let's suppose that each player I, knows their own valuation on this object, denoted as VI, valuation, but each player doesn't know the other player's valuations. Okay, so and now we could see that the signal function will be something will be a map from the cross of all those values to their own value, right? So because the each player cannot observe anything about from the others. Okay, so and suppose that the set of possible valuations is the finite set V. Okay, this is a set of all the possible valuations. Okay, and each player has a belief that each other player's valuation is drawn independently from the same distribution over V. Okay, independently drawn from some same distribution, okay, over this V. Good. So it's just some prior belief, right? Okay, so we could model this now as a Bayesian game, and we could write down all those parts that consists of this Bayesian game. Okay, so this this is a Bayesian game. It includes the following parts. So the set N is N players from 1 up to N. Okay. And set omega, this is the set of states. And it is simply V to the N's. Okay. And that is the set of the profiles of the valuations. Okay, in this case. And that will be the state or the type, right? So the set AI, okay, A is the bits, okay, the actions. Okay, set AI actions of actions for player I. Okay, so this will be a positive real number, right? Okay, from 0 to infinity. It depends on how much you like this object, right? So if you have infinitely much of the money, and you like this object very much, you can bid for a lot, right? But as long as you have those money. So the set of signals, okay, Pi, that player I can receive is V, right? Okay. And there's a signal function. Okay, was it? It's denoted as tau I for player I is defined by this tell I, as we just mentioned in the beginning. So the inputs are all those states or those types, and the output will be just the state for player I, because player I cannot observe anything about other players, but the player I could perfectly observe their own valuation. Okay, so and about the prior belief. So for the prior belief, let's use PI for that, of player I is given by this probability, so which is should be the product of all those priors that we defined previously, right? For each of those valuations drawn independently from this same distribution. So Vi up to Vn, and it will be this is not pi, this is a product. Okay, for player J from 1 to n, and we use this little pi for Vj. So this little pi will be the distribution, okay, prior for some PDF or probability distribution pi over this V. Okay, good. So what else? We also need this preference relation, right? Preference relation defined. Remember that defined over the cross of state and action, right? So here, this preference relation is represented by the expectation of the random variable whose value in the state or in those V's, and that will be so the utility will be defined as the how much you like this object Vi minus the price you need to pay if you win this object, if you win this auction. So by the rules of the second price auction, if you win that, then you only need to pay the second highest bid in this auction. Okay, so you don't need to pay the first the highest bid that you just bid. Okay, so you only need to pay the second highest one. Okay, so it's represented by the expectation of the random variable whose value in state V or V1 up to Vn is as follows, is Vi, okay, so your valuation minus how much you pay, so it will be the maximum over player J in all for all the other players excluding player I and AJ. Okay, so the second highest bid for among all the players, so excluding the player I itself. Okay, and this is if I is the player with lowest index for whom where this AI is greater than or equal to AJ for all the J's. Okay, and this player has to pay 0, so it doesn't need to pay anything or pay 0 if this player doesn't win. Okay, and 0 otherwise. So those are the rules for this second price auction and the corresponding payouts. Okay, so and we want to argue that this game has a Nash equilibrium. In this case, it would be the Bayesian-Nash equilibrium. Okay, so B and E. So it will be bid or the action A star, where this A star of player I Vi, it exactly equals to this Vi. Okay, for all the I's and for all the VI's. Okay, each player bids his own valuation in this case. Okay, so and we will show that it is a weakly dominant action for each player to bid their own valuation in this case. Okay, so to show that, okay, so now we'll have a rough proof that for that. Okay, so suppose player I doesn't bid their own valuation but bids something else. Let's say bids this BI. Okay, so now we split this into two different cases. Okay, so first, if this BI is greater than the player's valuation, okay, so the first subcase would be that, okay, so this VI is smaller than BI, right? And let's say if those both are smaller than the maximum bid or the maximum valuation of all the other players, okay, let's say for J not equal to I and Vj. Okay, so in this case, so we see that although this BI is greater than VI, okay, but it doesn't affect anything because now in this case, this player I still loses this auction and doesn't pay anything, right? So payoff will be still 0, okay, and it's still the same as the previous payoff when having this VI or bidding this VI, right? So it doesn't matter, okay. But and we also want to check the other case if we know that this VI is less than this BI, right? Let's suppose if we move this max VJ to the other side, if this max VJ, J not equal to I, if that is smaller than those two things. So if that's the case, and it's still okay, right? So because in this case, it also doesn't change this thing because this player I, if this player I previously bids using this VI, then pays the maximum of the others, but now since this player is still paying the second highest bid, so it doesn't matter if this player is bidding something higher than that. Okay, so that's still fine. So this payoff is still VI minus max VJ, right? J not equal to I. Okay, still the same as before. Same as before. Okay, and same as before. Okay, all good. So the problem happens when it's in the between, right? So now we have those two different cases, but if we put that max Vj, J not equal to I, if we put that in between of those two things, between of Vi and Bi, right? If we do that, put that in between, then we find that then this will change the outcome of this game, right? Because now this player I is bidding too much, right? So this will change the outcome that previously this person will lose that auction because this person I doesn't want the object that much, right? But here, since this BI is even greater than the maximum of VJ for J not equal to I, then this player now this player I is winning the auction actually, right? So but the valuation would be still VI. So this person is paying something extra and the utility becomes negative, right? So the payoff now equals to still VI minus max VJ. So the payoff structure doesn't change, right? We have that. But here this value changes. So now it becomes negative. And that is lower than the previous payoff when this player was bidding VI and just gets 0, right? So now it gets a negative payoff. Okay, so it becomes worse. Okay, so now this happens. This will be the problem, right? Okay, so this is the first case that we discussed. If BI is greater than VI, and it'll be symmetric, right? If there are still some problem if BI is less than VI, right? And now we could similarly argue as before. So in the first sub case, so in the first two sub cases, there will be no problem. But if we put that in between, then there will be some problem, right? So in the first sub case, where we say that is max Vj, we put that on the left. That is, let's suppose that is smaller than Vi and smaller than Vi. Okay. So in this case, the payoff would be Vi minus max Vj. Okay, and that'll be okay, right? That'll be fine since that doesn't change anything. Okay, same as before. And the second case, subcase, would be that Vi is smaller than Vi, but we put max Vj to the other side, and that is still the same, right? And now this would be a zero payoff, right? Because this person is losing the auction. Okay, so same as before, it doesn't change anything. But in the third case, if I put that max Vj in between, okay, in between, it means that we have this Vi on the left and Vi on the right. Okay, so now the payoff would be it'll be Vi minus max Vj, right? So now, so previously, so here, be careful that previously this person beats Vi, right? But now this person is beating this, player I is beating this Bi, okay? So now it changes the outcome such that this player now is kind of losing this game, right? Because that is smaller than this. Okay, so in this case, this payoff would be this Vi minus some max Vj, and so which is so this player actually is bidding less, right? So and the player I should have bid more than that, right? So now this payoff would be this Vi minus the maximum of Vj, where this j now equal to I. Okay, and that'll be lower. Okay, lower than the payoff. Okay, run payoff from bidding this Vi and winning, right? And the reason is because that now this player, I really want that object, but actually is bidding less than that. So now this player is losing this this object, right? Okay, so good. So now we have argued all those different cases where the where this we complete all those different cases where this where we prove that this strategy where this player I is bidding their own valuation will be the equilibrium strategy. Okay, and that will be symmetric for all those players since each player they have the same belief and they're with this independent distribution from all those valuations. Okay, so each player will be symmetric in this case. So here we form this Basic-Nash equilibrium, where in the second price auction with the sealed bids, so each of the player bids their own valuation in this case. Okay, so that'll be a good example for the Bayesian game and Bayesian-Nash equilibrium. So later we'll also introduce some other examples in the next episodes.